Let's go ahead and summarize intermolecular forces and get a decent overview as to what types of molecules will have what types of intermolecular forces. So as we start to look at these, dispersion, if you recall, was the first intermolecular force that we talked about. We said that this was the weakest of all of the intermolecular forces. And what we're doing here again for these intermolecular forces is we're assuming we have similar molecular weights. So for dispersion, this was whenever we had an interaction between two nonpolar species. And I'm going to abbreviate nonpolar as NP. So we'd have nonpolar with another nonpolar molecule. And if it was only these two nonpolar molecules interacting, we would say that the only intermolecular force is dispersion. We know that anything with electrons has dispersion in it, but for things that are nonpolar, this is the only intermolecular force that they have. The next type of intermolecular force, as we start to go up, would be a dipole-induced dipole intermolecular force. So whenever we see the word dipole, we're going to think polar. Whenever we see the word induced dipole, we're going to think nonpolar. So if it's dipole-induced dipole, this is just another way of saying, well, it's an interaction between a polar and a nonpolar molecule. So the polar species will induce a dipole on a nonpolar species, and these interactions can be slightly stronger than dispersion, although if there's enough electrons, dispersion will still be stronger. After this, we get to ion-induced dipole. So if you see the word ion, you should probably be thinking that there is an ion present. So we'd have an ion mixed with a nonpolar species. And in this case, the ion will induce that dipole on the nonpolar species, and this interaction is stronger than polar or the nonpolar species in its place. So before we go any further, I want to look at the hierarchy here. So notice that all of these have nonpolar in common. So what we can try to do here is just have a decent overview, a decent generalization, and we can say in general, ions are stronger than polar molecules, which are stronger than nonpolar molecules in terms of their intermolecular forces. And then we could actually predict the rest of this table on its own. So we've already exhausted nonpolar interactions, so the next strongest interaction would be looking at polar. Well, if we had a polar-polar interaction, that's what's actually next. It's a dipole-dipole interaction. And these are slightly stronger than ion-induced dipole interactions. After that, we have a special type of dipole-dipole interaction. Remember hydrogen bonding, where we have FH, OH, NH, and then we have that hydrogen bond going between those. So that's a special type of dipole-dipole interaction, and it is stronger than the typical dipole-dipole interaction. So after this, now we've exhausted all combinations of polar interactions. So now we could have ion polar. So ion polar would be slightly stronger than hydrogen bonding and dipole-dipole. And an example of this may be if you have something like a sodium ion and then something that has a dipole in it. So like whether that's HCl or H2O, anything like that. And then finally, we get up to ion-ion interactions. And this would be more or less an electrostatic Coulombic interaction between two ions. So to summarize this, dispersion exists between all molecules. There's a greater significance in the forces whenever you have different molecular weights, okay? So whenever I ask you to compare intermolecular forces, I'm always looking at similar molecular weights. I'm not going to ask you to compare a protein to a water molecule and ask me which one has stronger intermolecular forces. What we'll also see is that the forces associated with the permanent dipoles involve the electron displacement in the bonds, not the molecule itself. So for instance, we could end up having HCl. The electrons are shifted over within the bond, okay? It's not going to shift within the entire molecule. If you had something that might look like this, if we had, actually let's change that chlorine to a fluorine. We had NF3 okay, so we have these electrons that are being distributed more towards the fluorines. But again, they're just being shifted within the bonds, not the entire molecule. So what we can say from here is if you have similar molecular weights or similar molar masses, if you have a dipole force, that's going to be stronger than dispersion. Okay, so dispersion will be classified as the weakest of the intermolecular forces here. So let's go ahead and get an overview, a few examples of these. So if we look at a couple of molecules, the first thing you want to do is you want to draw out Lewis structures and determine the polarity. So CH4 looks like this. As we start to look at this, are all the terminal atoms the same? Yes, they are. Do we have any lone pairs on the central atom? No. So that means that this molecule is nonpolar. If we were to look at HCl, we could draw this Lewis structure. And for HCl, what we'll end up seeing is chlorine's more electronegative than hydrogen. So the electrons are displaced. So there's a dipole pointing towards the chlorine. So this is a polar molecule. NH3, we draw this Lewis structure. Looks something like this. Although all the terminal atoms are the same, there's a lone pair on the nitrogen. So that means that this is a polar molecule. If we were to look at H2O, the terminal atoms are the same, but there's lone pairs. So this is a polar molecule. We have methanol, so CH3OH. You have to draw your skeleton out and then fill in your lone pairs and bonds appropriately. But what we'll see is this molecule here is definitely not symmetric. This over here with this OH group, that's going to be more electronegative. So this will be a polar molecule. And then finally, if you have sodium chloride dissolved in water, we know that sodium chloride would dissociate into the sodium and chloride atoms, or ions, excuse me. And then we'd end up with H2O, with the waters being attracted towards the sodium, the oxygens of the waters, because there's that lone pair. And then for the chloride ion, it would be the hydrogens of the water molecule that would be attracted towards it. So what I want to do now is we'll go and compare what kind of intermolecular forces are present whenever all of these interact in different combinations. And we'll figure out what are the weakest, what are the strongest. But before we do that, I want to look at sodium chloride and water. So with sodium chloride and water, what we'll end up seeing here is you have sodium chloride, which is an ionic compound, and water, which is a polar molecule. So if we are looking at the interaction between sodium chloride and water, we're not looking at water molecules interacting with other water molecules. If we're looking at sodium chloride interacting with water, we would say that the strongest intermolecular force that is present here would be ion dipole. That's the strongest intermolecular force because the sodium chloride forms ions and the water is polar, so it's an ion dipole. There's also dispersion present, but the ion dipole is the stronger of the intermolecular forces. So let's go ahead and look at some interactions between these molecules. So here, if we have CH4, so recall that CH4 is nonpolar, HCl is polar, ammonia is polar, and H2O is polar. So if we have methane, so CH4 interacting with another methane molecule, it would be two nonpolar molecules interacting. So in this case, the only intermolecular force that would be present would be dispersion. Now, if methane were to interact with hydrochloric or hydrogen chloride here, so we know that methane is nonpolar, HCl is polar. So in this case, we would have dispersion, because anything with electrons has dispersion, but we would also have dipole-induced dipole. So the strongest intermolecular force for an interaction between methane and HCl is dipole-induced dipole. And we would see something similar for methane interacting with NH3, and then methane interacting with H2O. All right, so let's go ahead and jump down to HCl interacting with HCl. So in this case, these are both polar molecules. So if you have a polar molecule, you need to ask yourself, can this thing hydrogen bond? Well, you have FH, OH, or NH. Well, we don't here, so there's no hydrogen bonding. So we know that there's dispersion because there's electrons. Okay, so then since it's a polar molecule, if you have one HCl molecule interacting with another HCl molecule, it would also exhibit dipole-dipole intermolecular forces. So that would be the strongest intermolecular force that's being exhibited here. If you have HCl interacting with NH3, it would be the same thing. We'd have dispersion and dipole-dipole. Because again, we're not considering NH3 interacting with NH3. And the same thing with water. So now let's get down to ammonia, NH3 interacting with another NH3. So here we have electrons, so we know we have dispersion. Then it's also a polar molecule. Some people put dipole-dipole down, some people don't. I tend to. But then since we have NH on both of these, there's also hydrogen bonding. So if you have NH3 interacting with another NH3 molecule, we would have hydrogen bonding present. If we have ammonia NH3 interacting with H2O, well, we have dispersion and dipole because we have two polar molecules interacting, but since we have NH and OH, this is also hydrogen bonding. And the final example is water, which we've talked about a ton. So if you have H2O interacting with another H2O molecule, we have electrons, so we have dispersion. They're polar, so it's dipole-dipole. And we definitely know that there is hydrogen bonding. So hydrogen bonding is the most prevalent of the intermolecular forces here. So some questions that may be asked of you as we start to look at intermolecular forces and how they manifest themselves and other properties would be looking at vapor pressure or looking at boiling point. So what we'll say is, the stronger the intermolecular force, the higher the boiling point. So if you have something that has hydrogen bonding versus something that has dispersion, the species with hydrogen bonding would have a higher boiling point than the species that only has dispersion. We'll also see that boiling point is related to the vapor pressure. So the stronger the intermolecular force, the lower the vapor pressure will be. And we'll come back and we'll start to look at vapor pressure at the molecular level as we move along. But these are the main types of questions that we'll ask in terms of how does intermolecular forces affect something that we can measure more readily in lab. And so these are the two things that we'll look at. But make sure that you can draw your Lewis structures. So we'll just make a list of steps. Step 1, draw your Lewis structure. Step 2 is polarity. And then you need to go through your chart that was given on the first slide of this video and determine what kind of intermolecular force there is. So remember, if you were going to try to pair these up and you were going to try to reproduce this table, we could start from scratch. So if we were considering all the things, we know that we'll end up with a nonpolar species, a polar species, or an ionic species. If nonpolar is the weakest and ionic is the strongest, we could build our way up. So the weakest of the weak would be nonpolar, nonpolar. Then we would have polar, nonpolar. Then we would have ion, nonpolar. Okay, so now we've used up every possible interaction with nonpolar. So the next strongest would be polar interacting with another polar. And then this is the only one that doesn't follow the pattern. This is hydrogen bonding, because this is a special type of dipole-dipole interaction. So hydrogen bonding, so we have FH, OH, and NH. And then after that, we'd have the interaction of polar with an ionic compound. I guess we'll write the strongest one first. And then finally, we'd end with ion-ion as the strongest. So you don't need to know these energy values at all. If you can think about the relative strength, that is where we're at. So hope this helps.